Gian complex example 4.3-3 Heat loss by convection and conduction and overall U. Problem goes saturated steam at 257 degrees Fahrenheit is flowing inside a 3/4 inch steel pipe having an internal diameter of 0.824 inch and outer diameter of 1.050 inch. The pipe is insulated, so it's insulated with 1.5 inch on the outside, of course, and the convective coefficient are given. Hi for the steam, it's equal to 1000 BTU per hour feet square degrees Fahrenheit, and that on the outside of the air, it's equal to 2 BTU per hour. And we're also given with the metal thermal conductivity of the steel, and we also are given with the uh, we're using this one. We're using British 226 BTU per hour, and we're also given with that of the insulation, which is 0.037. In this case, we are simply asked for what will be the heat loss per 1 foot of length of pipe if the surrounding air is at 80. And again, we're being asked in letter B, we're being asked to recalculate the problem using the methods of overall heat transfer coefficient based on the internal area. So to have a good grasp on the problem, allow me to draw a rough sketch of the problem. Okay, so here's the rough sketch of the problem. We have saturated steam entering through this pipe. It enters at a temperature of 267 degrees Fahrenheit. And actually, it is assumed that throughout the pipe, the temperature of the steam is essentially constant. And since it's hot, it will, heat will be transferred from the steam through the pipe wall, through the lagging, and into the air, where air here is actually, the air is quite cold, or essentially it's only at 80 degrees Fahrenheit. If you'll ask, well, if the steam is, releasing heat to the air, why is its temperature constant? Well, there will be change of phase only, like steam will become liquid water. It will still be at 267 degrees Fahrenheit. So now the problem looks simple. We're just asked to find for the heat loss. How much heat is flowing from the steam to the pipe and through the air. Okay? So essentially, this will look like I'm drawing here also a cross-sectional sketch of that. And essentially here we have here, this is our pipe, okay? Our pipe, the internal diameter of our pipe, and since our pipe has a certain thickness, so this is like the outer diameter of your pipe, and since we have a lagging, meaning an insulation to it, this is like the outer diameter of your insulation. Okay? Well, in this case, we could label this as our Ri, the internal diameter, and this one, we just label it as R1, the like, internal radius, I mean. R1 will be the radius of the outer radius of the steel pipe, and R3, let's just label R3 as our external radius of our lagging. So this problem really looks like, conduction through cylindrical pipes in series. But the only thing that's different here now from previous discussion is that there is now involved convection. Because here, what is given is not the temperature at the inner surface of your pipe. What's being given is the temperature of the bulk of the steam, which is the one flowing inside the pipe, and the other given is not the temperature of this one, not the temperature of the outer layer of your insulation. What is given is that the temperature of the surrounding air. In this case, the surrounding air, the bulk of the surrounding air here is at 80 degrees Fahrenheit. In this case, the flow of heat could be traced as the heat flows from the bulk of the steam towards the inner wall of the pipe, and then to the outer wall of the steel pipe. So as it has reached here, it needs to what? To be conducted to the outer wall of the insulation. And from here, it needs to be conducted to the surrounding air, finally. So this is at 267 degrees Fahrenheit, and this one is at 80 degrees Fahrenheit. The temperature here of the inner wall, let's label this at T1. Temperature of the outer wall, let's label that as T2. Temperature of the outer wall of the insulation, this one of the green, we'll have it labeled as T3. So we don't know T1, T2, and T3. What we know is only the bulk steam temp and the outer surrounding air temp, which is at 80. This one, bulk steam to inner wall, we have here convection. Convection is different from conduction because here the fluid could actually move by density differences, meaning in conduction it's only the electrons that's moving, but in here it could be thought of like the molecules really of the fluid, like the steam here it actually is moving towards the wall or something like that. So this convective heat transfer. An inner wall to the outer wall, we have of course that conduct, because this is what a solid that's made of steel, and outer wall to the outer wall of the insulation like this. It seems like inner insulation to the outer surface area of the insulation. That's still what conduction, because the insulation is of course a solid material. And finally, from the outer surface of the insulation to the bulk of the air, that's now convection, because air is a fluid and it can move. Really, it could go near to it and it could actually move out, carrying more heat. So from that's convection. So as what we can see, we have now a mix of convection and conduction. But we could just really treat this, a process as, yeah, a transfer through series of resistances. Okay, we could really just do that. And allow me now to introduce a new way of solving resistances in series by using the analogy of electrical resistances. So let me drag this down and I'll be drawing now. It seems like we have four resistances. The resistance to convection, we call that Ri. Resistance from the center to the surface, we call that resistance Ri. And then the resistance from the inner steel pipe to the outer steel pipe, let me call that Ra, resistance through the steel. And then the other one, resistance through the insulation, like outer wall of the steel pipe to the outer wall of the insulation, let me call that Rb, just to be consistent on how does the Ganco please book label this one. And finally, from the surface to the bulk of the air, let's call that resistance as Ro. So it seems like this one now will have values like the temperature here at this node at 267, and the temperature here is at 80, and we know this degrees Fahrenheit. And similar to electrical circuits, we can really lump this into a single resistant, lumping all the resistances in series, calling that R total. Okay, and this one now will be at 267 degrees Fahrenheit, and this one is also at 80 degrees Fahrenheit. And to compute for Q then, with a very let's try to have analogy with the electrical circuits. It will be I is equal to difference in the voltage delta V over the resistance. In here we'll then be having simply as Q, the heat flow, which what we would like to calculate, equal to delta V. In this case, delta T, the difference in the temperature, delta T, simply 267 minus 80 over what? R total in this case, a total thermal resistance. More or less, the big deal now will not be the delta T, but the major concern is how do we calculate these resistances. Okay, now let's try to evaluate first Ra and Rb. We choose this first because I think we're familiar already with conduction to cylindrical walls. And to calculate the resistances, let me drag this down a little bit. It will not be relatively simple. So like Ra would just be what? Well, the thickness of the steel pipe, delta R, over the conductivity of the steel, like A refers to the steel, and area log mean of the steel pipe. In this case, if we put values to Ri, R1, which is, let me just put that here. Well, if you, since we are given with ID of 0.824, let me convert that to feet and divide that by 2, so to convert it into radius. So Ri will just be equal to 0.412 over 12, right? Because I divide by 2 already. So I'll have it here 0.412 over 12. R2 by R1, which is supposed to be the radius of this part here, the outer um, radius of your steel pipe. R1 will be 0.525 over 12 feet, and R3 will be 2.025 over 12 feet, because we are also given that the pipe insulation is 1.5 inch thick. So we manipulate that, and then we are getting, I hope that you'll be able to get this by yourself. How do you evaluate, or how do you find out what will be the outer radius of this whole setup, like the outer radius of your insulation? Now, delta R will simply be, well, the thickness will just be R1 minus Ri, okay? R1 minus Ri, and values are already given on the, okay, it's already given for steel. We are given with some values of K. The area lag mean will be more or less not that straightforward to compute, but could be calculated really from the definition of, well, area lag mean will just be, well, if you are getting the average area of, two logarithmic area of two values, then you simply have here a1 minus a2 over ln of a1 over a2 if you're calculating for the logarithmic mean of a1 and a2. In this case, if we have Ra, we'll be calculating for the log mean of inner, this one, inner area over and the outer area of the steel pipe. And doing that, following that, Ra will be just be equal to 0.00148. Similarly, Rb will just be, then will then lead to a value of 5.80. Okay, so it's really expected, meaning I'm actually jumping into the final answer to this. I'm not showing the lengthy calculation for this one. So if you like to take a look, Ra is way much smaller than Rb, because of course your steel pipe is not an insulator. It's a good conductor of heat, while the insulation will giving it a very high, like relatively high resistance, 5.80 compared to 0.00148. So that's really the purpose of insulation. It gives you a resistance to heat transfer. Now for convection, the thing is that we are following the equation for convective heat transfer. This one, the transfer of heat Q is just equal to the convective heat transfer coefficient H times the area exposed to the convective transfer times delta T. Okay, this one, very simple equation. This is the equation for convective heat transfer. And if you'd like to convert this format into our standard Q is equal to delta T over R, well, delta T looks the same, and more or less we'll have this term, okay, equivalent to this term. Of course, there could be thought of one of that, which means that HA could be thought of equivalent to 1 over R, right? Since Q and Q are just the same here. Or in this case, really, the resistance offered by convection is just equal to reciprocal of that, R, that will then be what? 1 over HA. So this is now in resistance form. How do you get the resistance, thermal resistance of a convection heat transfer? Okay, simply 1 over HA. Now, when we refer here to H now in this case, for example, the steam here into the inner wall of the pipe, we are given actually here the internal heat transfer coefficient, meaning that's what we have in there. Okay, for Ri, for example, determining Ri, it will just be equal to 1 over Hi, the convective heat transfer coefficient of the steam. because steam is the one here that we have here. Steam at 267, and it's what? Transferring heat to the inner wall of the pipe. And the area we're talking here is the area of the wall, inner wall of the pipe, AI. So that's what we do with that. And not really much of a problem if we got that already because the values are already given. AI is easy to solve, simply 2 pi Ri times the length of the pipe. And if we substitute the values to it, we could actually get 0.00464. Okay, the resistance offered by the steam is 0.00464. Similarly, for the air outside the pipe, because the heat transfer will be, there will be convection from the steam here to the inner wall, and when the heat now reaches this outer wall of the pipe, it needs to be transferred to the air, and that's also another way of convection. So we have there R outer, the resistance offered by the air will just be 1 over HO, the convective heat transfer coefficient of the air. And in this case, HO is given by this 2 BTU only. HI here is 1000. 1000 HI means the steam is conductive, meaning it could transfer heat readily, while HO, low value of HO, meaning uh, it has a poor convective heat transfer coefficient. So the cold air doesn't really has that high capability to transfer heat by convection. And if you do the math for this one, HO convert to the value for HO, and for the AO, the outer area of your insulation, will then be getting a value of 0.472. So as you can see, this one compared to this one, the air offers a higher resistance because it doesn't offer a good convective heat transfer, while for the steam, its resistance is small. And of course, if you want heat transfer, then you want this, okay? If you want heat to flow, but if you don't want the heat to flow, then you would like to have a higher resistance. So now I think we're ready. We already have calculated for Ri, Ra, Rb, and Ro. And to compute now for what? For Q, we simply use this Q is equal to delta T over Rt. Okay? So R total, what is R total now? Well, we simply add everything. The Ra, because electrical resistance in series, the total resistance will just be the sum of the individual resistances. So we'll have here Ra 0.00148 plus 5.80 plus this and plus that. That will then give us 6.278. Okay, 6.278. And then if we calculate for Q, the flow of heat, we'll simply use this formula really. Okay. So let me just drag it here and let me put that. The Q, amount of heat that is lost every feet really, because we're being asked calculate heat loss for 1 feet of pipe or 1 foot. So we'll have here delta T. What's the driving force? The total driving force is 267 minus 80. Okay, minus 80. Then the total resistance is given to that 6.278, and that will then give us a value of 29.8. Of course, the unit will be BTU, meaning British thermal unit of heat per hour, meaning this insulated pipe will lose this amount 29.8 BTU every hour per foot of that pipe. Okay, so this is the answer, and that's not really much of a problem. The only more possible complication here is how do you calculate for the resistances using the area? How do you identify the proper area in calculating for the area log mean, which area to use? So it takes really practice to do that. And for letter B of the problem, it asks for repeat the calculation using the overall heat transfer coefficient UI based on the internal area. What do you mean by that? Simply, The Q could also be calculated not using the resistance form, but it could be used like lumping the convective heat transfer and the conductive heat transfer. One could just generalize the equation into Q equal to U A delta T. Okay, UA delta T. And in this case, if you base, if you choose a representative area, since we are talking about here two areas exposed to your fluid, in this case, the inner pipe is exposed to the steam, while the outer, this area here on the outer of the insulation is exposed to the air. One could just thought of, well, if you choose one of that, meaning in this case we're choosing the area which is the inner area, that means that the overall heat transfer coefficient that you're calculating is also based on that inner area. We also label it as UI. Okay, and I think we're given here some values already for, no, we already know what is delta T. Delta T is simply the difference of the total driving force. In this case, well, we know that the fluid flowing inside your pipe is at what? That's at 200 something, 267, this one, and the air is at 80 only. So 267 and 80. So the driving force is already known. In this case, delta T is simply 267 minus 80. Well, AI is also easy to calculate, right? Because not much of a problem, because it's just based on this area, and the area of this one will just be the inner area of the steel pipe is just 2 pi Ri times the length of the pipe. In this case, well, 2 pi times, well, the radius of that is just Ri is just 0.412 over 12. Okay, 0.412 over 12, and then length of the pipe is just 1 foot. So we are actually getting a value of 0.2157, 0.2157 feet square. Not really much of a problem with the area. So the only problem here is how do you calculate for UI? Well, evaluating this one, we already have solved the problem using the terms of resistances. Well, this equation is just still equivalent to delta T over R total, right? Really, not really much of a difference with that. So in this case, if we equate that to, we'll be getting what? Delta T, we'll be getting UI AI delta T will just be equal to delta T over R total. And in this case, delta T and delta T will cancel. And UI is just what? How do you calculate for UI? UI will just then be equal to 1 over AI times R total, right? Which means that you could just calculate the resistances and then multiply that by the uh, area which we are referring to. In this case, since this is based on the internal area, multiply the resistance with the area internal, and then get the reciprocal. That's UI already. Okay? Okay, so in that case, we could just simply calculate for UI, since, or if we have not done this, we know the resistances in the individual resistances Ri, Ra, Rb, and Ro. Simply sum that up to get R total, which in this case we already know the R total, right? This is 6.278. Multiply that with AI. Okay, multiply that with the AI and get the reciprocal of that. That will be the UI already. Okay, so essentially it seems like, well, having that here, well, AI here is just what, 0.2157 feet squared. UI will then be equal to, if we try to calculate really, AI is 0.2157 here multiplied by the R total, which is 6.278. 6.278, and you're getting a UI, the universal or overall heat transfer coefficient based on the internal area equal to 0.738. And that's what you put here, 0.738. And then, of course, you'll be supposed to be getting the same answer, 29.8. The only difference in this approach, this one and this one, this is based on uh, heat transfer, overall heat transfer coefficient. This is based on resistance, but I would like to prefer resistance. I'll be using a lot of resistance approach than this one, unless you are already given with the overall heat transfer coefficient. Because the only thing that is um, preferable with this approach is that there are already a lot of tabulation for the values of the overall heat transfer coefficient for some practical engineering devices. Okay, and that's it. Thank you.